Welcome back to the deep dive. So you've been building this amazing foundation, right? Looking at atoms, molecules, bonds, solutions, states of matter, the real building blocks.
That's a good way to put it. You've got the static picture, the what is it made of part.
Exactly, but now things start to get dynamic. We're moving into the realm where chemistry really happens, change, reactions.
Precisely. This is where we shift from what matter is to how it transforms. Reactants turning into products. And you really can't talk about transformations without talking about energy.
Yes, energy, that seems to be the key. So this deep dive, we're focusing on this chapter that really kicks off that whole discussion, aren't we?
We are. It introduces the concept of heat of reaction. And honestly, this is the absolute starting point for understanding the energy story behind chemical changes.
So our mission then is to sort of unpack these core ideas, the definitions, the principles around this heat of reaction.
Yeah, because getting this right is fundamental. It tells us why some reactions go and others don't, how much energy is involved, and sets the stage for, well, pretty much everything else.
And you mentioned this as a jumping off point. It connects to other big topics later on.
Oh, definitely. Understanding reaction energy now. It's crucial for tackling things like spontaneity, will a reaction even happen on its own? And kinetics, how fast will it go? And equilibrium, where does it end up?
Right, and I remember seeing a note that calculations start becoming more prominent from here on out.
They do.
So let's jump in. This whole area of heat and energy in chemical systems, what's the big field called?
We're entering the world of thermodynamics.
Thermodynamics, okay.
The chapter defines it pretty clearly. It's the study of heat and energy and how they interact within all sorts of systems. Chemical ones, obviously, but also physical and biological.
So it's kind of the science of energy flow.
In essence, yes. Its real purpose is to help us answer questions about how energy gets transferred, how heat is exchanged, how matter transforms. I mean, it underlies almost everything we observe.
It sounds fundamental. You mentioned it applies broadly.
Oh, absolutely. From engines to ecosystems to the reactions happening in our own cells.
And this field has some guiding principles,
Yeah.
laws, I think.
That's right. The laws of thermodynamics. They're like the non-negotiable rules for energy and matter in the universe.
Okay.
The chapter mentions three, but for our focus today on heat of reaction, the first law is really the star of the show.
The first law, okay, I feel like that's one people might have heard of. What's the main takeaway?
The absolute core concept is energy conservation. Simple, but profound. Energy is neither created nor destroyed. It only changes form. It transforms. The total amount of energy in the universe.
Yeah.
Constant.
So when wood burns and releases heat, that heat energy wasn't made. It was already there, just stored differently in the wood and oxygen.
Exactly. It was stored as chemical potential energy in the bonds, and the reaction converted it into thermal energy, heat, and light. It's like cosmic bookkeeping. Energy changes accounts, but the total balance stays the same.
Okay, that makes sense. Conservation.
Yeah. The chapter does nod to the second law, which deals with entropy, or disorder, always increasing, and the third law about behavior, near absolute zero temperature. They're part of the bigger picture.
But for heat of reaction, the first law, conservation, is our anchor.
It's the foundation. Energy in equals energy out, just maybe in different forms.
Got it. So energy changes form. When we're looking at chemistry, what specific forms of energy are we most interested in?
Well, the broad definition of energy is the capacity to do work or produce heat. And this chapter really zooms in on the heat part, the heat that gets transferred when the chemical reaction happens.
Okay, focusing on the heat transfer. And the chapter breaks energy down into potential and kinetic.
It does. Potential energy is stored energy. Think of a ball held up high. It has potential energy due to its position. In chemistry, the energy stored within chemical bonds is a critical form of potential energy. Depends on the arrangement of atoms, the composition.
Right, the bonds themselves hold energy.
And kinetic energy is the energy of motion. Molecules aren't static. They're constantly moving, translating, rotating, vibrating. That movement is kinetic energy. Okay, so here's the chemistry link. Chemical energy is a form of potential energy. It's literally stored in how molecules are built in those chemical bonds.
Exactly. And when a reaction happens, old bonds break, new ones form. That rearrangement can release the stored potential energy. It can then do work, like contracting a muscle, or just be released as heat.
The source then brings in this idea of internal energy, often shown as U or E.
Right. That's the total energy inside a system. It's the sum of all the kinetic energy molecules moving, vibrating, and all the potential energy stored in bonds within that system.
So when a reaction occurs, the system's internal energy changes.
Correct. If the system gives off energy, maybe as heat or by doing work, its internal energy goes down. If it absorbs energy, like taking in heat, its internal energy goes up.
The source uses a great comparison. Cells using glucose and car engines burning gasoline.
Yeah, it's a good one. Both take complex molecules, high in stored chemical potential energy, and break them down into simpler ones, like CO2 and water, which have less stored energy.
And that difference in energy has to go somewhere, right? First law.
Precisely. It's released. In the cell, it powers life processes, work. In the engine, it pushes pistons, that's work done by the system, and a lot escapes as heat. You need that radiator. The energy is conserved, just changed from potential to kinetic and heat.
Okay, so understanding this conservation and transformation is key, but let's connect it more tightly. Why is this concept so vital when you start really digging into chemical reactions themselves?
Yeah.
Predicting them, controlling them.
This is where the theory gets really practical. The source points out several key reasons. First off, predicting reaction behavior.
Knowing if it gives off heat or needs heat.
Exactly. Exothermic, releasing heat, or endothermic, absorbing heat. This tells you a lot about whether a reaction is likely to happen spontaneously, how much energy you might need to kickstart it, or how much you might get out.
Helps you guess what'll happen in the flask.
Yeah.
What else?
Second, optimizing reactions. If you know it's exothermic, maybe you need cooling to control the rate. If it's endothermic, you know you need to supply heat. Understanding the energy helps you tweak temperature, pressure, things like that to get the best yield.
Makes sense. Controlling the conditions.
Third, and this is huge, safety.
Right. Uncontrolled energy release. Bad news.
Very bad news, especially in industry. You have to know the heat of reaction to design safe equipment, cooling systems, emergency procedures. Think about large-scale polymer production, often highly exothermic. Get the thermodynamics wrong, and you risk dangerous runaway reactions.
Okay, safety is critical. What's next?
Fourth, environmental impact. Energy isn't free. Designing reactions to be more energy efficient or finding ways to capture waste heat, that's all guided by thermodynamic understanding. It helps reduce the environmental footprint.
Good point. And finally,
Lastly, product development. The energy involved in making a material affects its final properties. Think about creating strong alloys or specific ceramics. The synthesis energy influences their structure, their stability, their performance. Understanding enthalpy helps chemists design routes to materials with the properties they want.
wow, okay, so it really does touch everything from basic prediction to industrial safety and advanced materials. Now, the first law covers all energy, heat, and work. But this chapter, and our focus now, zooms in on the heat part.
Yes, and that brings us to enthalpy change, symbolized by delta H. AH.
And the key definition here is
It's the heat of reaction measured specifically at constant pressure.
constant pressure. Is that a common condition?
Very common. Think about reactions happening in an open beaker in the lab or large industrial vessels open to the atmosphere. They're essentially under constant atmospheric pressure.
Ah, okay. And when pressure is constant, how does AH relate to heat?
Under constant pressure, the change in enthalpy, FH, is equal to the heat flow, which we often call Q subscript P, QP. So AAH equal QP.
Got it, which is why heat of reaction and enthalpy change are often used almost interchangeably in this context.
Exactly. Assuming we're at constant pressure and mainly concerned with heat, not other forms of work like gas expansion against a piston.
And mathematically, how is AH defined in terms of the reaction?
It's simply the enthalpy of the products minus the enthalpy of the reactants.
And the sign at H tells you immediately whether it's releasing or absorbing heat.
Yep. If AH is negative, H products is less than H reactants. The system lost enthalpy, releasing it as heat. That's exothermic. Think combustion, feels hot.
And if AH is positive,
Then H products is greater than H reactants. The system had to gain enthalpy, absorbing heat from the surroundings to make the reaction happen. That's endothermic. Think melting ice or those instant cold packs that feel cold.
okay, so we know what AH means, what its sign means. Now for the practical bit, how do we actually put a number on it? How do we calculate the amount of heat?
Right. The sources lay out two main ways. First method, using thermochemical equations.
These look like regular balanced chemical equations, but they have that AH value written next to them, right?
Exactly. And that AH value corresponds specifically to the molar amounts shown in that balanced equation. The source uses methane combustion as a classic example.
CH4 gas plus 2O2 gas gives CO2 gas and 2H2O liquid, and the AH is 8 of 90.3 kilojoules.
Perfect. The negative sign confirms it's exothermic. And that value, next is 890.3 kiloj, is the heat released when exactly 1 mole of methane reacts with 2 moles of oxygen to form 1 mole of CO2 and 2 moles of liquid water.
The IH value is locked to that specific stoichiometry.
Precise.
So let's say you have a specific amount, like the example asks.
No.
How much heat do you get from burning 10.0 grams of methane, assuming you have enough oxygen? How do we use that equation?
It's a standard stoichiometry problem, just with energy added. You
Got it.
start with the mass, convert to moles, then use the H value as a conversion factor linked to the moles in the equation.
Okay, step 1, grams to moles. Methane, CH4, the molar mass is about 16.0 grams per mole, so 10.0 grams of methane.
1 mole CH4, 16.0 grams CH4, grams cancel, now you have moles of methane.
Step 2, moles to energy. The equation tells us 1 mole of CH4 releases 890.3 kiloj. So that's our next conversion factor.
Right, you take the moles of CH4 you just found and multiply by 890.2 kiloj, 1 mole CH4. Don't forget the negative sign because heat is being released.
Units cancel out grams, moles, leaving kilojoules.
And the calculation gives you 556 kilojoules. So burning 10.0 grams of methane releases 556 kilojoules of heat. The minus sign just confirms the release.
Straightforward. The source mentions another example with SO2, but the process is identical. Mass to moles, then moles to kJ. It seems straightforward, but you absolutely need to pay attention to the units and use the correct mole ratios from the balanced equation. It's a core skill for these upcoming topics.
Okay, so we can calculate heat for direct reactions if we know the NH, but what if a reaction is really hard to measure? Like maybe it's too slow or explosive or makes a mess of side products?
Ah, yes, good question. There's a very elegant way around that using something called Hess's law.
Hess's law, okay.
And the reason Hess's law works is because enthalpy is what we call a state function.
State function, right.
Yeah.
You mentioned that. It means the change depends only on the start and end points, not how you got there. Like climbing a mountain, the total elevation change is the same no matter which path you take.
That's the perfect analogy. Because enthalpy works like that, Hess's law follows directly. It states that the total enthalpy change for a reaction is the same whether it happens in one single step or in a series of multiple steps.
So if you can piece together a target reaction from other reactions whose H values you do know,
Then the H for your target reaction is simply the sum of the H values of those individual steps you used. A for-all equals the sum of the H steps.
that seems really useful.
It is. Its main power, as the chapter highlights, is finding the age for reactions that are impractical to measure directly.
Precisely. The source uses the example of finding the heat of formation for sulfur trioxide, SO3, from sulfur and oxygen, SS plus 32O2G, SO3G. Maybe this is hard to measure directly.
But maybe we do know the age for burning sulfur to SO2 and for burning SO2 to SO3. We can combine those known equations.
Yes, but you often need to manipulate the known equations first, and there are rules for that.
Rules like, if you flip a reaction around, reverse it, you have to change the sign of its EH.
Correct. And if you multiply an entire equation by a number, say double it to get the right number of moles, you must multiply its AH by that same number.
Okay, this explains the calculation shown in the source example for SO3.
Exactly. Seeing that division by 2 is a huge clue. It means the original reaction that had a 8H of a nitrogen under 97.8 kiloj wasn't used as written. It had to be divided by 2. Maybe it originally formed 2 moles of SO3, but the target equation only needed 1 mole. So you divide the entire equation by 2, and you must divide its ES by 2 as well.
Final answer of negative 395.7 kiloj for the formation of 1 mole of SO3 directly from sulfur and oxygen.
Correct. Hess's law lets us find ERH values for reactions indirectly, using data from other easier-to-measure reactions. It's incredibly useful.
It's a powerful calculation tool based purely on enthalpy being a state function.
Very clever. The chapter also gives that formula using standard enthalpies of formation.
It's another major application that stems directly from Hess's law and the state function nature of enthalpy. If you have tables of standard enthalpies of formation, which is the enthalpy change when a mole of a substance is formed from its elements in their standard states.
You can calculate the H for almost any reaction.
Exactly. Again, without necessarily doing the experiment. It's a calculation shortcut derived from these fundamental principles. Understanding what eta is and that it's a state function is key to using that formula correctly.
Okay, this is making sense. So let's try to wrap this up for you, the listener. We've covered quite a bit, moving into this world of chemical reactions and their energy.
We started with the big picture, thermodynamics, the study of energy, and zeroed in on the crucial first law. Energy is conserved, it just changes form.
Right. We looked at different energy types, potential stored in bonds, kinetic in motion, and how they combine into a system's internal energy.
And we spent a good chunk of time on why this matters. predicting reactions, optimizing them, safety, environment, making new materials. Understanding energy change is incredibly practical.
Then we got specific with the heat of reaction, especially enthalpy change, AH, which is the heat exchanged at constant pressure.
We saw how it's calculated conceptually, H products minus reactants, and how the sign tells us immediately if it's exothermic, negative H, heat out, or endothermic, positive H, heat in.
And crucially, how to use thermochemical equations. They give you the A for specific mole ratios, allowing you to calculate the heat for any amount using stoichiometry. Grams to moles, then moles to kJ.
We walked through that methane calculation as an example.
And finally, Hess's law. The idea that because enthalpy is a state function, you can find the age for a tricky reaction by adding up the age values of known steps that sum to that reaction. A very powerful indirect method.
Plus, we noted how the standard enthalpy of formation calculations are built on the same foundation.
So as you continue your studies, remember this chapter is foundational. Getting comfortable with defining, calculating, and interpreting age is absolutely essential for what comes next.
Yeah, topics like spontaneity, kinetics, equilibrium, they all rely on this energy understanding. And yes, they will involve calculations, specific terms, variations, but they all connect back here. This is the energetic language you'll be using.
Definitely. So here's something to chew on. We know energy is conserved, just transformed. Chemical reactions are one major way this happens. Think about that principle, energy conservation, and how it might apply to every change you see. A battery powering your phone, food giving you energy, the sun warming the earth. How does this initial look at the heat involved in simple reactions hint at the universal energy balance driving everything around us and even inside us?
It's all connected by energy flow. And now you're starting to see how chemists measure and predict it.
Keep thinking about those energy transformations.